All right, ready to do some quantum gravity. So, and we'll do quite a bit more of this before this presentation is over. So, we're going to use three parameters: Planck's constant, Newton's gravitational constant, and the speed of light. These are three parameters that dominate what's done in any calculation that involves quantum mechanics. That's Planck's constant and associated gravity. So, a question is, what is the characteristic time associated with these three parameters? All right. Planck time is the time required for light to propagate one Planck length, and we're going to talk about that next. But using these three parameters, we can do this calculation. In a prior slide, you saw h with a slash through it, like this one. This one does not have it. They're virtually the same. One is h over 2 pi. That's what that slash mark means. So it's Planck's constant divided by 2 pi. It's depicted this way. So we have three parameters. Each has its own units. Here they are. So now we're going to construct time, which I borrowed this from somebody else's presentation. Actually, this right here is the reference. He uses S for time. So time to the 1, and here's the same formulation we've been using. So we have h to the alpha, g to the beta, c to the gamma. We do our arithmetic, and we get equations for alpha, beta, and gamma. And there's some arithmetic to do here. And we end up with alpha equals a half, beta equals a half, and gamma equals 5 halves. So we get this, that the characteristic time using these three parameters is h bar g over c to the 5th. Turns out that we always put proportionality here because we don't know what the numerical multiplier is in general using dimensional analysis, but in this case it's actually an equal sign. This computation to get this result gives you exactly the right result. So the Planck time, 10 to the minus 44 seconds. Just make the following point. If you want to do this problem rigorously from first principles related to quantum electrodynamics, you could spend 4 years as an undergraduate and then at least 2 years of graduate school before you're in a position to actually do this calculation and get this result. And we managed to do it in about 35 seconds. So, and incidentally, Planck, who was prominent, of course, or Planck, who was prominent 120 years ago, he knew about this idea that you could combine these three parameters. Of course, he was the one that introduced this constant to explain blackbody radiation using his what at the time was a revolutionary idea of quanta, that light was quantized. And of course, he knew about gravity and the speed of light. He knew about this and combined these, and he got this result, and it was just, its relevance was not clear at that time. It's taking more and more time. So, just a little history there. So, let's look at a more comprehensive list of Planckian calculations using dimensional analysis. For example, what is the Planck mass? We're going to use the same three parameters and construct something using our technique. Here's the technique right here. Here's all the math. If you want to calculate mass out of these three guys, you get this. CH over G with a square root. And indeed, you get a small, but curiously not microscopic mass. This is about the mass, as indicated here, of a flea's egg. So it's not tiny. I mean, compare that with, here's the Planck length computed using the same method, 10 to the minus 35 meters. Planck energy, which you might imagine, is equal to this times c squared, the Planck energy is 2 to the times 10 to the 9th joules. That's about the equivalent of the energy in a full tank of gas. So even though, as we saw here, the Planck time is exceedingly short, and the Planck length is very short, the Planck mass implies a Planck energy, which is macroscopic. You would notice this if somebody handed it to you, because it's the, as I say, the energy in a tank of gasoline. Here's some additional information on the physical interpretation of combinations of H, G, and C. And they appear in all kinds of mixtures of this type in calculations in general relativity. But using dimensional analysis, we get the right answers. Oh, and I should point out, no proportionality constant is required here. Using these three guys, we do get the Planck mass, the Planck length, and the Planck energy. How about if we calculate the velocity of expansion of a universe dictated by matter? And here's the typical thing we're talking about. This is the velocity of expansion. So you have to have a velocity here constructed out of these parameters, and you get this expression for the velocity. Radius of the universe. The same kind of technique is used. Notice this. So if the universe is dominated by matter, mass, you get something that depends on the size, the radius of the universe, the size. You get t to the 2/3. I see a little error here. See that v, that's not right. That should be something, a parameter like r. Yeah, for radius. So this is a well-known result from the so-called de Sitter model of the universe formulated by Einstein and de Sitter right after the Einstein field equations were published. So growth at t to the 2/3. Density of the universe. So we put units of density over here, matter per cubic length. Once again, same process, same algebra, and here we get the density of the universe goes as 1 over g times t squared. Notice the total mass in the universe for this kind of model doesn't appear in the result. The density is dictated by time and Newton's constant. The mass has a exponent of 0. These are all kind of interesting results, and here's a paper that's available through arXiv. If you haven't used arXiv, you might want to explore that. So the distance scale, what is the characteristic distance if you use g and some mass m? We'll tell you in a second what that means. And once again, I've reverted to c to the c, which is bad form, but we'll just be careful. So the characteristic distance here turns out to be this, gm over c squared, and that's half of the Schwarzschild radius of a black hole of mass m. So we're missing a factor of 2 here, but we get the distance scale associated with these parameters, and it is a property of black hole. In terms of times, a characteristic time for these parameters, we get this, gm over c cubed. This is the time it takes light to travel the distance of the Schwarzschild radius to the horizon of a black hole. I mean, it's just this distance divided by c. Right? We had a c squared there, and now it's a c cubed. Now, I promised earlier we were going to talk about hydrogen atom again. So let's say we have hydrogen atoms bound by gravity. Is there some mass of those atoms that is somehow critical? And we are going to exploit, this is a quantum mechanical problem, so Planck's constant, speed of light, Newton's constant, because it is a gravity problem. They're bound by gravity, and the mass of a hydrogen atom. Once again, we have 4 parameters and 3 equations, but let's go through it. And we do some arithmetic, and we can say this. We don't know what gamma is, but alpha is minus gamma, beta is minus gamma, and delta is 1 plus 2 gamma. So we get this structure here, still not knowing gamma. Now, at this point, you'd have to stop. But it turns out that this is correct once you find out that gamma is equal to minus 3/2. You get this. And this is the Chandrasekhar limit of the mass that causes something dramatic to happen, namely a sun of this size, about twice our sun's mass, collapsing to a neutron star. Of course, once again, to get this result, you have to have an independent way to figure out gamma. I haven't seen that kind of problem done, but if gamma is minus 3/2, there it is. I think the actual determination of gamma comes from the Chandrasekhar's work in quantum mechanics and dealing with the degeneracy associated with the Pauli exclusion principle. So there's some deep science required to get this result. But we were on the right track. We're on the field, as they say. Okay. So we're coming to the end here. I want to just emphasize dimensional analysis provides a lot of insight if it's done right. To do it, you have to have some concept of the physics involved in the problem you're working on, and you have to know the physical constants that are pertinent. But if you do those things, you can get results that are otherwise would involve a lot of calculation and possibly learning a whole new field of science or engineering. So that's the end of the formal presentation. There are a few more slides. Let's go through those. References. And, oh, actually, maybe that's it. I apologize. So, anyway, thanks for your attention, and hope to see you soon.